In this video, we are going to learn what is the multinomial logistic regression. We will also learn how to perform a multinomial logistic regression in SAS using an example. So let's get started with theory first, and then we'll go to how to perform the multinomial regression in SAS. Okay, so what is multinomial logistic regression? So this is a kind of logistic regression. If you're familiar with logistic regression, you can easily understand what is the difference between the multinomial logistic regression from the normal logistic regressions. So as you know, in normal logistic regression, we normally a model for the categorical variables, and in logistic regression, the categorical variables, which is the dependent variable, takes only two values, right? So the dependent variable takes always values of 0 or 1. Okay, so that's logistic regression. So in multinomial logistic regression, we extend that to multiple categorical values. So it will not be just 0, 1, 1. It will be more than two categories. Okay, so it's used to model categorical dependent variable, and the dependent variable takes more than two categories. Okay. So there are more than one category, or I would say there are more than two categories for the dependent variable, and the categories cannot be ordered. So the example, the example are like the choice of color. So what makes somebody choose one of the color out of a given set of colors? Choice of profession. So what makes people to choose a certain profession? Choice of undergraduate program. So there's so many undergraduate programs. So what makes people to choose a particular program? So these are typical examples of the multinomial logistic regression, or examples where multinomial logistic regression can be used for study purpose. Remember, in all these cases, we'll have more than two categories. Okay, if there are only two categories, we can go for simple logistic regressions. For more than two, we need to use the multinomial logistic regression. And remember one thing, in multinomial logistic regression, the categories cannot be ordered. So when it comes to choice of color, let's say they're red, there is yellow, and then there is green. You cannot actually order these colors, right? They're of same strength, so you cannot order them. Similarly, choice of profession, somebody want to be an engineer, doctor, lawyer, so you cannot order them in any way. Similarly, any undergraduate program, whether it's physics, computer science, history, you cannot order them in any way. So multinomial logistic regression is used where you cannot order the category. You cannot order or sort the categories. If you can sort the categories, then we'll use another type of logistic regression known as the ordinal logistic regression, and we'll see that in another tutorial. Okay, so that's totally a different topic. Okay, so now let's compare how multinomial logistic regression is different from the simple logistic regression theoretically. So unlike logistic regression, which has got two categories, independent variable, the multinomial will have more than two categories. So one example that we will take for this demonstration of this concept, we'll take an example of choice of streams or choice of undergraduate course in college. Okay, so our dependent variable is stream. That means which stream the student belong to, or a student is choosing which stream of subject or which category of subject in the undergraduation. So our dependent variable has got three values. One is physics, second one is computer science, third one is economics. So the objective of study is to find out what makes people choose subjects like physics, computer science, and economics, and what is the order of choosing physics over computer science, physics over economics, and so on. So that's the idea about the study. So the independent variables, we have taken two independent variables. One is economic status of the student, and the marks scored in school. So marks scored in mathematics. Okay. So that's two independent variables. So economic status is a categorical independent variable, whereas marks scored in school exams is a continuous independent variable. Okay, so I've got two independent variables, one categorical, the other one is continuous, and we'll see how the study goes. So the sample data looks like this. So I've got the dependent variable stream, which has got three categories, 1, 2, 3. So 1 means physics, 2 means computer science, and then 3 denotes for the economics. Okay, so we have just used three numbers to denote the three different choices of undergraduation course. And we've also got two independent variables. One is status. Status takes value of 1 and 2 and 3. So 1 is lower economic status, 2 is little better than the first, and then the third is the highest economic status. And then mathematics score in school examinations is a continuous one. So that's out of 100. How much? What is the score of the student out of 100 marks in school examinations? All right. So in this particular type of scenario, in this kind of problem, what are the possible choices that you have? What kind of techniques you can possibly use? One way to solve this problem, or one way to model this data, is to use the discriminant analysis. So if you're familiar with discriminant analysis, the linear discriminant analysis, popularly known as LDA, you can also use that, because LDA, or linear discriminant analysis, also takes care of multiple categories of dependent variable. So that's also useful for categorical modeling. The other techniques could be you can actually convert or transform this this data into a two category dependent variable data. So instead of three category, you can simply transform it. You can actually delete one of the data types, or you can simply say, let's say you can combine one and two categories and then call it as one, and the third category as two. So from three categories you just come down to two. But there's a problem with this. Well, you can come down to two categories and then you can use logistic regression. But the problem is that you will be losing data, or you'll be losing information. So that's not a very recommendable technique. The third one is the multinomial logistic regression, which we are going to use in this case. So in multinomial logistic regression, we'll have multiple loggards for a single variables. Unlike in logistic regression, where there were only two categories, there were only two categories of 0 and 1. So we used to have these loggards as logarithm of probability of 1, divided by probability of 0, right? So that used to be the loggards in the logistic regression. Now when we have three categories, 1, 2 and 3, so what are going to be the loggards? Well, the loggards will be logarithm of probability of 1 divided by probability of 3. We'll assume 3 as the base category, and then the other loggards will be logarithm of probability of 2 divided by probability of 3. That means the category 3 is considered as the base category, so we're comparing the loggards of somebody choosing a particular subject. So loggards of 1 compared to 3 and loggards of 2 compared to 3. So 3 is the base category. Now base category can be anyone, like you can choose 1 as the base category, 2 as the base category, and so on. So that's about so if you have like 3 categories, you will have 2 loggards, right? Like in this case we have got 2 loggards, right? So you have n number of categories, you will have n minus 1 loggards. So that's the idea. So we'll have n minus 1 loggards for n categories in the dependent variable. So we've got two loggards in our examples. So one is so what is the loggard of somebody choosing physics over economics, and what is the probability or the loggard of somebody choosing computer science over economics. So economics is considered as the base category in this case. So you can choose physics or computer science as well. So we'll also see how you can actually interchange the base category when we do that, do it in SAS. So we'll have two intercepts because there are two loggards. So we'll have two intercept and two slope coefficients for each one of these variables. Why? Because to get the probability, you'll always have one for a particular type of comparison. So when we compare 1 and 3, we'll have one intercept. When we compare 2 versus 3, we'll have another intercept. So we'll have two, like in this case, when there are three different three different categories, we'll have two types of regression equations. So the first one will look like this, second one will look like this, where we'll have beta naught and then beta naught dash, beta 1 and beta 1 dash. So they're going to be different because the dependent variable comparison is actually changing. Physics compared to economics in the first case, computer science compared to economics in the second case. So we'll have two intercept, two slope coefficients and on. And if your independent variable is categorical, so you'll have again another category of slope coefficient, because for each category of your independent variable you'll have another separate. So status has got 3, so you'll have again 2 into 2, that is equal to 4 estimates for status, because there are 3 categories, so you'll have again two more categories over there, which is again it's same in any kind of regression. Every time you have categorical variable in your independent variable set, you will have multiple categories of a multiple number of slope coefficients. So we'll see that when we do it in SAS. Let's go to SAS and let's try to do this. So whatever we learned in theory, we'll just apply it in example. So the example that I have explained to you, we'll just take the same dataset. So I'm going to show you the dataset first. This is the student dataset, which has got 200 observations or information for 200 students. We've got 3 variables. One is the economic status of the students, and the second one is the stream or the undergraduate course that the student had selected for his undergraduate course, and the third one is the math score or the mathematics score of the student in school. So these are the 3 variables in front of us, and stream is going to be the dependent variable for us, which has got 3 values, 1, 2 and 3. 1 stands for physics, 2 stands for computer science, and 3 stands for economics. So hope the data you have understood the data. Now let's try to start with some basic descriptive statistics. So let's see what is the distribution of students across these 3 streams. So across these 3 streams, 45 of the students belong to physics group, 105 are from computer science, and 50 are from economics. Okay, so that's the distribution of data. So what is the distribution of economic status among these 200 students? So 47 students come from backward status, which is represented by 1, and then 95 of them come in the middle category, and 58 come in the elite category, or better or the best economics category. And we'll also see how the mathematics score is actually varying with respect to streams. So so is there a difference between whether mathematics score is influencing people to choose a certain category of streams? So here you go. So we'll see that for stream 1, which is physics, the average math score is 50, For computer science, the average math score is 56, and for economics, the average math score is 46, which is pretty logical, because people with good math scores tend to go to science and math topic like computer science, like physics, whereas people with less quantitative ability go for subject like economics or any other social science. Alright, so you can use proc frequency and proc means to be able to understand the distribution of your dataset. Okay, alright, so we'll straight away go to the modeling part. So we'll use proc logistic to do the multinomial logistic regressions. The syntax for multinomial logistic regression is very similar to what you have done in the normal logistic regression. We'll use the proc logistic and then data, and then we'll use the dataset student. In the class statement, we need to provide what is the class or class variable involved here. So there are two class variables. So class variable is nothing but the categorical variables. We've got two. One, the dependent variable one, and the other one is the independent variable. So stream is the one and the status is the one. Alright. In the model statement, we've got the stream as the dependent variable, and we've got two independent variables, status and math. And then we'll use a link function, which the link function says that we are going to use the generalized logic link function, which will takes care of the multiple categories in dependent variable. If you do not use this, the model will find it difficult to provide you the multiple multinomial logistic regression. So ensure that you use the link function. Link is equal to glogic, which is generalized logistic function or link function. Okay. And then we are going to save the probability score for the data points. Now, if you have done logistic regression in SAS, you are familiar with the output statement. So, in the output statement, we simply save the the input data set with the probability scores. So, once the model is built, the model will be used to score the data, the same data, and then we'll use that to compute the probability score, and we'll save that score in the data set. So, we'll also see an interesting thing in the logistic in the data. So, we'll run proc logistic and let's see the result. Alright, so like any other SAS procedure, it starts with the model information, what is the dataset and how many variables are there, what is the optimization algorithm which is used, the model uses generalized logic, the optimization technique uses Newton-Raphson, total number of observations uses 200, and you'll also get the response profile, that means the distribution of your different categories for the dependent variable, and the next one is the reference category. So remember that we have not given any information about the reference category. We have not said which category is to be considered as a reference category or the base category, right? So by default, it has taken the last categories as the reference category. So stream is equal to 3. That means the subject economics, because 3 stands for economics, is taken as the reference category or the base category. So computer science will be compared to economics, and then physics will be compared to economics. Okay, so third category is the base category. So by default it is taken. We can actually change it, and we'll see how we can change the reference category. The next one to see is whether model is converged, also, which is important to see. So in multinomial logistic regression, you have to be a little more careful with the model convergence status, because many times it doesn't converge. So ensure that you check the result, check it in the result before going ahead with the interpretation of statistics. And then there are some model fit statistics. Like in any other type of regression equation, you will get the AIC, the SC, and the -2 log L value. Okay. So you'll get all three model fit statistics, which can be compared across models to select the best model. And the next one is the testing of the global null hypothesis. So all three global null hypotheses in this case are significant, both likelihood ratio, score, and Wall statistics, because the p-value is less than 0.05. So what is the importance of global null hypothesis? So it tests that at least one of the independent variable is contributing towards explaining or variation in the dependent variable, or one of the important at least one of the independent variable is actually making significant contributions. So this is important because if the global null hypothesis is not satisfied, or if any one of the test is not valid or it's not significant, then you cannot go ahead with the interpretation. So that's the first thing to say. So that's also is good in this case. And then another important and the most important in the result is the analysis of maximum likelihood estimate. Multiple values for intercept and multiple values for the slope coefficient, multiple estimates. So the intercept 1 is -3.3, which is also significant because the p-value is less than 0.05. Intercept 2 is also significant, which is having the value of -6.89. Now, when you have 3 categories in the different variable, you will get 2 intercepts. If you have like 4 categories, you will get 3 intercepts. So if you have n categories, you will get n-1 intercepts. Okay, so that's the idea. Status is a categorical variable, so it has again got 3 categories of status. So you will get 4 estimates in this case, 2 for status and 2 for the dependent variable. Okay, so 2 multiplied to 2 is equal to 4, so you'll get 4 estimates. Dependent variable 1, status 1 estimate, and then dependent variable 1, status 2. Status 3 is considered as the base, so 1, 2, again another estimate, and then dependent variable 2 status 1. Sorry, I'm saying the I'm slightly confusing here. Dependent variable is this one 1. So you can see that dependent variable 1 and then status 1, you have got one estimate. Dependent variable 2 and then status 1 is another estimate. Similarly, dependent variable 1 and then status 2, dependent variable 2 and status 2. So status 3 is taken as the base category. So you will have 4 estimates for status, right? So if you have like 5 categories in the case of status, then you will have 4 into 2, that is 8 estimates. So that's the way you will have it in results. Math is a continuous variable, so you will only have 2 estimates again, right, for 2 categories of dependent variable. So you've got for dependent variable 1, you will have estimates as 0.07, and dependent variable 2, you'll have estimates for as 0.15. Most of the estimates are significant except this one, status 1 and dependent variable 2. So it's not significant. Other than that, other estimates are all significant. And finally, you will have the odd ratio estimate. So odd ratio does the comparison of one estimate with the other, and you'll get the odd ratio. That means probability of somebody choosing physics, to probability of somebody choosing economics. So it takes the exponential, or it takes the exponential of the estimates. Okay. So you'll also get the point estimate and the confidence level of the point estimate for the odd ratio. So you can interpret the odd ratio pretty much the same way, the way you interpret in logistic regression. If you don't know how to interpret the odd ratio, watch the video on odd ratio on my channel. I have explained it in detail. So I'll not get into the details of how to explain odd ratio, but that's useful sometimes. All right. Now we have the results in front of us. One thing that we are missing here is that in normal logistic regression, you will have the model diagnostics like concordance, discordance, C-statistics and all. But we do not get anything of that type in the multinomial logistic regression. So how do we ensure that the multinomial logistic regression is a good model, or is performing well? Well, it's not that easy in multinomial logistic regression. So you cannot get C-statistics in multinomial logistic regression, or it's not going to give you directly. You can of course compute in your own way, which is not very standard. It has to be your own way of computing. But there are a few statistics that you can look at while trying to assess the performance of the model, or goodness of the model. So one is the pseudo R square. Now pseudo R square is not exactly as the R square in multiple regression. It's very simple. It's not it cannot be interpreted the same way the R square is interpreted in multiple regression. But the more the pseudo R square is, the better is the model. So that you can say it for sure. More the pseudo R square, better is the model. So pseudo R square can be used across models to find out which model is the best model out of the given set of models. You can also use the AIC and BIC values to see the model parsimony. So the less is the AIC, better is the model, or less is the BIC, better is the model. So ensure that your AIC and BIC are minimum and your pseudo R square is maximum. So that's the way you can compare models. So that these are some of the commonly used model goodness of fit statistics in multinomial logistic. Pretty much like any other modeling technique, you can have your training data set, you can have your testing data set or validation data set. You can perform your model in training data and validate in your validation data or test data. You can also perform the similar kind of thing in multinomial logistic regression. There's no issue with that, it is a better practice to have 2 set of data set, where one set you use for development purpose and another set you use for testing purpose. All right. Another thing that we wanted to say is, how do we change the reference categories? Now, all the time we may not be interested in knowing, the comparison with the default categories. Now, default category here is the economics. We want to see how somebody is, somebody's odd of choosing computer science is varying with respect to economics, and then with physics with economics. But what if we want to know somebody's odd of choosing economics with computer science, and then physics with computer science? That means we want computer science as the reference category. All right. So for that, in this class statement, we use the keyword ref, you can see, and then equal to, in single quote, put the reference category you want to specify. So we'll specify 2, which stands for computer science, and then we'll use the same syntax. And when we use, let's run this. So in the result, you will see now the reference category use stream is equal to 2. So earlier it used to be 3, that was the default one. Now we can use 2, and you can also use 1. So you can change it according to your wish. The last thing we'll see is, so what is there in the output data set? So let's open the out data. So we have saved the probability for a particular student belonging to a particular category of stream, and we'll see how we can sort of categorize students based on the probability. Now you see that in the out data you will have 600 observations. So we started with 200 observations, now we have 600. Now you might have this question in mind, then how come we have now 600 observations? Well, for each category you will have a separate probability value, right? So you have two estimates for each category. Now one is considered as a base category, right? So hence you will have three probability values, not just one probability. Probability that somebody belongs to category 1, some probability somebody belongs to category 2 and category 3. So the same student will have three probability of belonging to three different category or three different streams. So for example, in the first observation, the student 1, the first student has a probability of 0.22 that he belongs to category stream 1. Okay, so he has another category. Okay, let me have this problem here because stream, we have sorted it with respect to stream. So you will get the probability of a particular student, choosing response profile 1, which is physics, response profile 2, which is computer science, and response profile 3, which is economics. So for every student, you will get three probability for he choosing physics, probability of he choosing computer science, and probability of him choosing economics. Okay, so for every student, you will get three probabilities. So since there are 200 students in our input data set, you will get 600 probabilities or 600 observations for every student. You will have three observations where your probability value will vary for different courses. Now, how do you find or use this model for new data? Well, and if a new student comes and you want to score his probability, so you'll again get three probability. Okay, so probability that a new student is going to choose economics, physics, and computer science separately. The one which is maximum out of three, he is going to choose that one. So if probability for computer science is highest among these three probability for a given student, then he is going to choose computer science. Similarly, for another student, if it is probability for her choosing economics is the maximum, then she is going to choose economics. So that's the way you are going to use the multinomial logistic regression to model for categorical variables and ensure that the categories in the dependent variable should not be ordered. So if you can order them, then you should go for the ordered logistic regressions. So if you like this video, subscribe to our channel. You can share it with your friends. You should also visit our website, which is in the description sections. Thank you.